My name is Kareem Khalifa, and today's lesson will be an introduction to quantification.
I'll break today's lesson into two parts. First, I'm just going to give you the basic ingredients in using quantification. Second, I'll show you there's a few subtleties in translating the verb to be with the new symbols we have in this language. Let's begin with the ingredients. Here's an example of the kind of sentence we're now going to be able to express in first-order logic. Khalifa delights everything. Some parts of the sentence are already familiar to you from first-order logic. For instance, we already know that Similarly, we know delights is a predicate. Khalifa is represented by what we called, but it turns out that we don't yet have a way of expressing the word everything in first-order logic. That's what we're going to get to today, among other things. Now, it turns out that everything actually has two components that are represented in first-order logic. The first is what we call the quantifier. We might represent it with the every in the word everything. It tells us how many things Khalifa delights, and that's everything. Individual concept. The second part of everything is thing, and that's basically a variable. It's a placeholder for any particular thing that Khalifa likes. We'll get into this in a bit more. It's the most abstract concept, really, that we'll be dealing with today. Before. So to see how we formalize this, how we express this in first-order logic, let's start with something that we already know how to do. Let's just take a simple atomic sentence like Khalifa delights Cleo. As you can see, she's thoroughly delighted in this picture. So we'd represent that as follows. We'd put delights, open parentheses, Khalifa, comma, Cleo, close parentheses. Recall that we call this an atomic sentence. As we'll see, we're going to contrast that with atomic formulas in a minute. Now let's turn to our new sentences today, things that have words like everything and something and so on and so forth. We'll go back to our example, Khalifa delights everything. In first-order logic, the guiding intuition behind what's happening with universal statements of this sort is that we're saying, for all things, Khalifa delights that thing. What we'll do now is show you how to turn this rough sketch of what we've just said into something that's sort of the official language of first-order logic. So let's just start with the part that most closely overlaps what we saw when we just had the atomic sentence, which is we get rid of that for all things and we just see that we have Khalifa delights thing. So note in English, this isn't really a sentence, right? Khalifa delights thing is just kind of weird, right? What you need is you need to say Khalifa delights everything or something or the thing. It needs what's called a determiner, right? As such, this isn't a sentence when it's just delights Khalifa, comma, thing. Rather, it's what's called an atomic formula, which is almost a sentence, right? It's sort of like the skeleton of a sentence, and it just needs a quantifier to sort of drag it over the finish line. However, instead of using the word thing, in first-order logic, we use what are called variables. Typically, these are letters towards the bottom third of the alphabet. They start at T and end at Z. Sometimes they have subscripts. But usually we start with X just like we do in algebra with variables. And so if we wanted an atomic formula in first-order logic, it might look something like this. Delights, open parentheses, Khalifa, comma, X, close parentheses. So note, X just means thing, right? So we can see now that we're inching towards the official definition. What we say is for all X, Khalifa delights X. And that, in fact, would not be a formula, that would be a proper sentence. So we just need to add one more thing in order to get this thing to be in the official language of first-order logic. And we need to change that for all, which we had in English, into that upside-down A. But these things just mean the same thing. We're just translating into first-order logic. In first-order logic, we say for all with an upside-down A, which you may have seen in your math classes in high school. Okay, so that upside-down A is called the universal quantifier, and it tells us that Khalifa delights everything. But suppose that we wanted to say that Khalifa delights something. We have a quantifier for this in first-order logic. We only have two quantifiers, but of course, Turns out that there are many more determiners than what we can capture in first order logic. To say that Khalifa delights something, we use this symbol here, which once again you may have seen in math class, that backwards E. What this says is there is at least one x such that Khalifa delights x. Note that it doesn't say that there's exactly one x, just says there's at least one, right? Which is a way of saying some, right? There's some x such that Khalifa delights x. Okay, so it turns out that our universal and our existential quantifiers actually have different rules for how you translate the verb to be when you're going from English to first order logic. Let's talk about those and then we can wrap it up. So when you have a universally quantified statement, that is one with an upside down A, says for all or every or something along those lines, words like is and are typically translated with the arrow, with a conditional. And I'll give you an example. Suppose, for example, we say every student is happy. Now, if you just do a one-to-one mapping of the English onto the first order logic, it'll actually get you pretty far, right? You'll see that every corresponds to for all x, student is then going to correspond to student x, and happy is going to correspond to happy x. But you don't yet have a word for is. But it turns out that is best translated using the arrow. What this says is for all x, if x is a student, then x is happy. And that's the translation of every student is happy. So you can think of the is as corresponding to the arrow. Importantly, however, that doesn't work when you have an existentially quantified statement. There, words like is and are become a conjunction. They become an and, that upside down V. So, for instance, suppose that we have a Karen amongst these students who's just not happy for whatever reason, wants to talk to the manager. Then we could say some students are happy. We would translate that this way. There exists an x such that x is a student and x is happy. Right? So basically what this is saying is those other four students sort of meet that criterion. And you can see that each one of them are students and each one of them is happy. So it seems that that's the right way to translate it. So, summing up, quantified statements in first order logic introduce three new ingredients: universal quantifiers, existential quantifiers, and variables. Make sure that you can distinguish between atomic formulas, which aren't sentences, and atomic sentences. Second, remember how to translate is and are. You're going to translate it as an arrow with universal statements, that is with the upside down A, and you're going to translate it as an and in existential statements, that is with the backwards E.
Thanks, and I'll see you at the next lesson.